Together, we will look into the culmination of our semester-long journey, unveiling the final results of our rigorous experiments and insightful research. Let's delve into the findings and explore the significance of this project.
The site of the Inflection Point Pavilion is located on Pratt campus at the Cannoneer Court parking lot between two ITL storage shipping containers. Rotating the pavilion 20 degrees allows onlookers when approaching the site to observe and understand the form, while allowing the 12-foot clearance for cars to pass, providing an orientation that was collectively agreed upon to best depict the transition from a saddle to a dome from both north and west entrances to the site.
The final task in the studio was the activation of the structure. This was done through a series of events to promote the user's interaction with the pavilion. We designed posters to invite guests to the two events, Mind Your Waist and Clock In. Initially, we had the first event scheduled Tuesday morning. I arranged with Professor Eddie Becky, a Pratt Industrial Design professor focused on reuse and sustainability, to serve as the guest speaker. Unfortunately, due to construction delays, we were forced to cancel the event and reschedule for Wednesday. This was obviously not the ideal turn of events, but due to safety concerns, we decided as a studio that this was the best course of action. The following day, we did a sort of soft launch of the pavilion with Clock In. The structure was still being constructed in the process with the tight time constraint we were under, but almost served as a performance of labor that the event highlighted. Because of this, interaction with the event was limited, but we still had some interesting results. The questions at the event were as follows. How many hours did you spend on your last final? What was your most and least expensive studio? How much did you spend on your last final? How many all-nighters have you done this semester? Do you think you are overworked in school/the professional field? And finally, do you think you are underpaid or undervalued in the industry? Later that day, we had our main event, Mind Your Waist. We were delighted with the success, with an entire class and several students passing by in attendance. We started off the event discussing the body of knowledge to which the studio is based on, the thesis of Rupert Malsdek, and the research done throughout our investigations this semester. The topic of waste had been a crucial aspect of the project and explicitly intertwined with the material efficiency of linear folded strips. We then opened up the event to allow the guests to interact with the pavilion and answer the questions posited to them. The questions were as follows. Approximately how many pounds of waste do you produce a day/week? What do you see as the most problematic material? Does eco-guilt impact you as a designer? Is it too late to make environmental change? Who is responsible for mitigating ecological damage? And finally, are humans better at creating or destroying? Once the students stood up from their chairs, I found that the space in the structure did not allow for much movement with the chairs present. I think if we were to do this event again, I would propose the chairs being situated at the mouth of the pavilion. This would allow the audience to have a more comfortable space to move around and answer the questions without being forced to navigate around the chairs.
In our continued efforts to address concerns regarding the reduction of material waste, expounding upon the sentiments expressed during the Mind Your Waste event, several furniture prototypes were constructed from repurposed cells from the pavilion, which aimed to engage a speculative and viable opportunity.
Rupert's algorithm is created by Rupert Malacek. He is an architect, researcher, and current professor in Austria. His research explores the relationship between form, structure, performance, and material. His algorithm is folding a strip which is made of two parallel lines placed along a wedge, which is the angle of a plane where the strip is folded against. The strip is folded by alpha and dp. Alpha 1 is the given angle where you fold the strip. dp1 is the given angle of how much you fold the strip. The given angle is the angle where you decide on the variable. Alpha 2 is the driven angle where you fold the strip. dp2 is the driven angle on how much you fold the strip. The driven angle is the angle given by the wedge. Repeat the strip folding with the alphas and dp's until there is no more strip to fold. You mirror the strip to create the top strip and the bottom strip. Rotate and copy the wedges that has the top strip and the bottom strip, and until you make 180 and a 360 rotation. This is how you create a rotational body.
We learned that the algorithm starts to create a saddle form that continues indefinitely if folded along the y-axis. As part of our research, we start to change given variables as an attempt to find new forms and ultimately manipulating the algorithm to create a structure that can be inhibited and creates a form that would help engage users in the space. Throughout the semester, we as a group dove into creating forms that seemed interesting to us, as well as incorporating architectural components such as lighting, threshold, program, and site while trying to break the algorithm that Rupert had provided.
We broke the generated saddle form by trimming, mirroring, joining, splitting, and other operations to expand the boundaries of the algorithm. Throughout our explorations, we found limitations in terms of size, structural integrity, and points of failure. For example, sagging and leaning occurred in unsupported areas, addressed by different iterations of infills, end conditions, and footings. Crafting the form according to program, personal bias, and stiffness led us closer to our final chosen form.
For our final form, we went through a series of design manipulations that combined 3 saddles of 2 different algorithms. In earlier iterations, we discovered that a bump or dome-like form can be created by mirroring 2 saddles. Another saddle of a different algorithm is connected to the dome. This saddle algorithm was manipulated to produce a more dramatic and flared entrance. The end conditions of this saddle vary in length, resulting in an asymmetrical entrance.
The final phase preceding the transition to ACM fabrication include the pivotal milestone, the one-to-one cardboard test. This test marks a significant leap forward, transitioning from a mere 1/8 scale model and 1-to-1 scale partial component to an authentic 1-to-1 ring capable of supporting human activities below. Crucially, it incorporates insight we learned from the creation of the 1-to-1 cardboard footing and will be used for the testing of reinforcement rigidity. Based on the experience of having a thin fold line may cause later deformation in assembly, we decided to offset the fold lines to make the strips easier to fold. We tested several offsetting parameters and finally decided to offset 1/8 of an inch. After using Zong to cut the cardboard, we scraped the script that we got and removed some part of the folding areas to make sure the strips can be properly folded without causing deformations. The assembly of the 1-to-1 ring follows a sequence of sorting the strips components, scraping, the assembly of a cell, connecting the cells to form a ring. The assembly was smooth, but we later found the ring cannot stand on its own. Therefore, we used a tripod to support the ring and found the places that need more reinforcements by checking the cracks. Ultimately, we figured that the footing needs more reinforcement and adjusted designs to ensure the rigidity of the pavilion that we later used ACM to build.
The fabrication and construction of the ACM pavilion, we developed an assemblage instruction manual for future reproduction, consisting of Manual A, Saddle, Manual B, Dome, and Manual C, Keystone. The weaknesses in the cardboard prototype were overcome through increasing the width of strip tabs and riveting in the ACM construction. The most updated ACM components were included in all of the 3 manuals. There were also some major issues that we discovered during the ACM pavilion constructions, such as the following. First, difficulty in sorting. Second, misalignment of brace and strips. Third, component breakage due to overfolding. These challenges were resolved during construction through sorting component pieces within the same unit together, bolting 2 holes of the lower brace tab for better alignment, and using a jig to avoid overfolding. The solutions we came up with led to the successful construction of the pavilion in the end, which were also elaborated in the first 2 pages in the manuals for easier and more efficient reproduction later on.
The digital model is produced with thickness, tolerances, and rivet holes. Surfaces are extracted and unrolled. Line work of strips were organized with a nesting software to produce efficient cutting sheets. These sheets were then sent to the CNC and Zund.
For the base of the pavilion, we used 2x3s to form a frame of beams and girders. Following the shop drawings, beams and girders were cut to the required lengths and angles. Plywood sheathings were also cut to shape using a jigsaw. On site, gravel had to be moved around or added to flatten the landscape as much as possible. Beams and girders were arranged and fastened into place. After, plywood sheathings were arranged in place and fastened with screws. Once the ACM strips were cut, we sorted them according to the groups that the strips belonged to. The engraving of the ACM strips are scraped with a screw to remove more material so that we can bend the pieces more easily. While folding the tabs, if there was still a great amount of resistance, we would use the heat gun to gently heat the engraving. After all the tabs are folded, the strips are riveted together to form a cell. We referred to our catalog of groups and assembled the cells accordingly. Starting with the footing groups of the dome and saddle side, we rivet and attach the remaining groups sequentially until we reach the keystone. As the groups began to stack and the structure got taller, we employed a cantilever method using ropes to hold up either side of the pavilion. The ropes were either tied to the shipping container or to a weighted container. Lastly, the keystones are inserted and the ropes can be removed.
The Inflection Point Pavilion exemplifies a critical approach in the field of architecture, material exploration, and sustainability. Through meticulous site planning, algorithmic manipulation, prototyping, fabrication, and event activation, our team showcased a commitment to pushing boundaries and redefining conventional design protocols. From the initial challenges of navigating site constraints to the final realization of the ACM Pavilion and its subsequent activation through engaging events, each step of the process reflects a thoughtful consideration of form, function, and environmental impact. The project not only demonstrates the potential of computational design and material efficiency, but also underscores the importance of collaborative efforts in addressing contemporary architectural challenges and discourse.